So here is our concept zero, our first rule, and if we don't get this rule, all is lost. Okay, and that is that magnetic field. If we've got a big magnet like this, let's make a big ring magnet like this. Okay, magnetic field is from north to south, and so these big magnets like this are wonderful because you've got all of that magneticness, right? You might even put coils of wire around it, make an electromagnet. But magnetic field is from north to south. Is north to south, okay? B is the symbol for magnetic field. Well, actually it does because it's magnetic field. Magnetic field. It actually makes sense because it's magnetism is the first magnets were actually discovered in Wales. Okay, and where's my piece of magnetite? The first magnets were actually there's the original what?
The country whales.
Yeah, the country whales, not like whales as in like cows and whales. I'll pass this around. This is actually an original piece of the original magnet found in Wales, right? And and as you know, there's all sorts of Welsh words like lamb and comb. And comb. Do we say the B? Right. Yeah. So this is like the silent B, right? And so originally magnetism was spelled b'magnet, right? Okay. And they actually pronounced it, but it was actually pronounced cor. Okay, which doesn't even look like the way it's spelled like that, right? And then the actual, they believe also that the very strong magnetic field lines in Wales because of that original piece of magnetite, okay, actually caused them to spell things and pronounce them in totally different ways, okay? So there's a divergence of actual spelling. But there was a B in the beginning of magnetic, and it's just a silent one. You never pronounce B's right next to M's. Very rare, very rarely. I can't think of one case like that. Okay, so this is concept zero, is that magnetism, a magnetic field is from north to south. So if you look over here, okay, if you look at this guy here, the north pole is on the top and the south pole is on the bottom, and so because of this magnet, this fixed magnet, the magnetic field is down. Yes? Okay. So let's I think we're going to practice that a little bit, right? The magnetic field is from north to south, and the fixed magnet. I'm supposed to show you something with a Magna Probe and the fixed magnet. Okay. This is the most wonderful thing. These things are called Magna Probes. Okay. Don't worry too much. It's a fairly ominous sounding name, but basically it's just a very strong magnet. So don't stick it to metal. Okay. It's a very strong magnet on a gimbal. Okay. Which is, isn't that the store from Elf? Gimbals. Is there really a store called Gimbals? I don't know. Okay. But here's a magnet. The North Pole is pointing up, which means the magnetic field lines are going out of the North Pole into the south. They go from north to south, okay? And so this thing is going to trace out that magnetic field. Isn't that nice? It's like, ooh, isn't that neat? Right? So this thing shows us not the magnitude of the field, but just the direction of it. That's kind of cool. Isn't that cool? Is that cool? I think that's kind of cool. It's like, even out here, it's like tracing that field, isn't it? Yeah. Yeah, this is a big, strong magnet, isn't it? Look at that.
Yeah, how far out could it go?
Nope, that's too far.
Oh, kind of.
There you go. That's kind of cool, isn't that
So
cool?
what would happen if the Earth was switched?
Like right now?
Yeah, for electricity. Like instant.
Luckily, I think we all use like GPS now, so it's like instantaneously. I'm sure there would be like some cataclysm, some magnetic cataclysm. It would bring down all the power grids on Earth. I don't know, something like that. Okay. Now, here's the second thing, and this is the first of our right-hand rules. So everybody, pull out your right hand. There it is. Okay. The first right-hand rule is that if I have a wire, okay, let me move this magnet out of the way so it doesn't interfere. Okay, if I have a wire and I have a magnetic field, and this is a very, very weak phenomenon, and so to make it stronger, what I do is I have many, many strands of wire. Okay, so if I put 4 amps through this and I've got like 30 strands of wire here,
120.
I've got 120. I've got 120 amps of current flowing like this. And let me make sure that I've got this the right way. Indeed, I do, because last night I was like, uh-oh, this is a fail. It's not working, but I had it hooked backwards. Okay, I'm turning it up. I know 4 amps is, and it's not going to, it makes these wires kind of get a little bit toasty warm after a while. It'll handle 4 amps like that. Okay, what this means is that there's a magnetic field that wraps around these wires. It's sort of a weird thing. Okay, it goes in circles. It is annular. Okay, so if I take this and I put my thumb in the direction of the current, and I pretend to grab this wire, or I really do grab it, my fingers point in the direction that the magnetic field goes. That means that it's going toward you, this way, yeah. Okay. In fact, you can see that if I put this Magna Probe there. Do you see it's very weak, it's not nearly as strong as the other magnet, but it's turning around and around like that. Okay. How about on this side? Which way is it going to go? Pretend to grab it. Yeah, it's on this side. It's going to be toward you. In front of it, it'll be to your right. Yeah. On this side, it'll be right. So on this side, it's there. It is. Yeah. So the red arrow on this thing is the direction of the magnetic field. Compasses point in the direction of magnetic fields. Yeah. Isn't that cool? Okay. So wires themselves. This is our first right-hand rule, and let me just write it down because I know there's very visually oriented people. Okay. The first rule is for wires. Okay. You put your thumb as the current goes, right? And your fingers wrap. Fingers has an I in it. Okay. So if you wrap your fingers around the wire with your thumb in the direction of the current, your fingers wrap in the direction that the magnetic field is. And the interesting thing is, I think we actually have this formula, is that it actually drops off with 1 over r. It's not like 1 over r squared because it's a different geometry. It's not a point and a, right. So in this case, it's a 1 over r thing. Okay, so direction of field around a wire. Let's just try this. Okay. Well, okay, the current is going up, yes? Everybody take your right hand out. Put your thumb up. Wake up, Nina. There she is. There she is, all right. Okay, so in front of the wire, which way is it? It is, here we need a, here we have it. I don't know, there it is, right? In front of the wire, which way is it going? To your right, yeah? There we have it, okay. Next one. Yeah, there it is, yeah. That graphic. Okay, how about behind the wire? Which way is it? To the left. On this side, toward you. Yeah? There we have it. How about behind this wire? Thumb in the direction of the current. Your fingers are going up. Yeah? Which way is it around this wire? Well, let's see. Thumb down. I guess as seen from above, clockwise, yes? Yeah? As seen from below, anti-clockwise. This is totally different physics. Like, we did all this stuff with circuits, and they're all flat, and they, right? This is all vector, very three-dimensional stuff. We got a question. Say it again. What if it's like 3 wires? Are they all together, hopefully, pointing in the same direction? Then you could treat them as one. If you've got another wire here and then another wire, say, out here, okay, then you have to actually do like a vector addition of it, right? And of course the field is, is a circular field around them, and so you have to use your geometry to figure it out, and you can just add them. It just adds like electric field is the short answer. Okay. The second rule is with a loop of wire. Okay, so the second one is the loop rule. Okay, with a loop always acts like it'll act like a north and a south pole. Okay, so loops of wires act like a magnet. They've got a north and a south pole, and here is the way it works, and here's how you figure it out. Okay, consider this loop right here. Okay, if I take this loop right here,